Welcome to Lecture 10. Here I'm going to apply Newton's second law in 2 and 3 dimensions. All the richness and glory of what Newton's law has to say about motion gets revealed when we look at motion in 2 and 3 dimensions. So we'll be doing mostly examples here to give you a sense of how Newton's law applies. But there's another agenda here. I want you to come away really understanding why it is that, for example, satellites don't fall down, or why it is when I do the following demonstration. Take some water, pour it in this bucket, and whirl it around in a vertical circle like this. Give me a little while to get it going. Why doesn't the water fall out of the bucket? Is there some force pushing it up, holding it in place? That's a very common answer to that question. Is there some force holding a satellite up? Is there some force holding this ball up as I whirl it in a vertical circle? Why doesn't the ball fall down when it's at the top of its circle? Is there some magic special force holding it there? Absolutely not. If you insist in saying there is, you're being Aristotelian. You're not believing Newton's second law that says force and acceleration are proportional, and you're not recognizing that acceleration represents a change in motion, any change in motion, including a change in direction. It's changes in motion that are caused by forces, not motion itself. So I'd like you to come out of this lecture being a real Newtonian and really understanding why it is that that ball doesn't fall down, and in fact, why that's really not quite the right question to ask, and why the satellite doesn't fall out of its orbit, and why that's not the right question to ask, and why the water doesn't fall out of the bucket. Let's look at one more example. Here I've got something that you would see at an amusement park, a roller coaster with a loop in it. These are common things these days in amusement parks. High school physics classes love to go off to amusement parks and measure all kinds of things about their rides. Well, we're going to do that with this miniature car. I'm going to launch the car on this track. Down it will go, and we'll see what happens. So what happened there? What was going on as the car went through the loop part of the track? Was there some special force pushing it up against the track? Was there some extra force that I don't notice but is there? Some maybe centrifugal force that's pushing it against there? No, nonsense. The reason that car didn't fall off the track was because that car was obeying Newton's second law. It was undergoing motion. In particular, it was undergoing changes in motion which were entirely consistent with the forces acting on it. And there were only two forces acting on it. There were nothing mysterious, no centrifugal forces, nothing like that. And what I'd like to do in the rest of this lecture is analyze in detail situations like that so you can understand exactly what's going on, and you'll come out of that with a really much stronger appreciation for what Newton's second law says, and this essential Newtonian idea that force does not cause motion, but rather force causes change in motion. Earlier, in Lecture 8, we saw how to use Newton's second law in the case of one-dimensional motion, where we were moving along a straight line. And we didn't have to worry about the entire formalism of vectors because we just had direction positive or direction negative. Now we need to get a little more involved. And I'm going to begin by reviewing exactly what I said in Lecture 8 about using Newton's second law. How do we use Newton's second law? First thing we do is write down the law. F equals ma. Force equals mass times acceleration. Force being a vector quantity, so there's an arrow over it. A, acceleration being a vector quantity, so there's an arrow over it. Remember, again, when we did the anatomy of Newton's second law, the thing on the left was the net force, the sum of all the real physical forces that are acting on the object. And that sum is, in general, a vector sum. It may involve vectors that are at different angles and different orientations, and they have to be added vectorially. The right-hand side of Newton's second law, not a force. It's just the product of the object's mass with its acceleration vector. There is nothing else in the law but the actual physical forces acting, and they go on the left-hand side to form the net force, and then the mass times the acceleration. One of the biggest misconceptions students have in learning introductory physics is to think that there are extra hidden secret forces that we really haven't talked about that aren't physical forces, but nevertheless, they belong in Newton's second law. They don't. There are no such forces. And that's why I'd like you to banish words like centrifugal force from your vocabulary. So the first thing we do to use Newton's second law is to write down Newton's second law. F equals ma. Vector F equals m times vector a. Then we draw the situation. We identify all the forces acting on the object, all the real physical forces that are acting on the object. We rewrite Newton's second law with these forces now explicitly identified. What are the physical forces acting in this particular situation? Make sure you got them all identified. Make sure you add them up to represent the net force on the left-hand side of Newton's second law. Next, you got to get into kind of human convention. You have to establish some kind of coordinate system for being able to write down positions and accelerations and forces and things like that. If we're dealing with a one-dimensional situation, we can just use plus and minus for the two directions. If we're dealing in 2 and 3 dimensions, as we will be some of the time in today's lecture, we make a coordinate system that includes at least 2 coordinate axes. We rewrite Newton's second law in our new coordinate system, explicitly in that coordinate system, solve the resulting algebra, and we have the answer to our problem, the solution for whatever we're looking for. It might be the acceleration of the object. It might be some particular force we're trying to find. It might be the mass of the object. It could be any of the unknowns that we might have in a problem. So that's what we're going to do now. We're going to do several examples where we do the mathematics of using Newton's second law in these situations, and we do it quite rigorously. So let's begin with the mathematics associated with what just happened here, the car going around the loop track. What was going on there? So I'm going to ask the question in particular, how fast does the car need to be moving around the loop track to make it? Because if it's going too slowly, bad things are going to happen. Let's see what happens if it's going too slowly before we start the calculation. I started the car way up here, and it got all the way around the track. But what if I started here? Not good. You wouldn't want to be in the roller coaster when that happens. How fast does the car have to be moving in order to make it all the way around that loop? So let's find that out. So how fast? So here's an actual photograph of a loop-to-loop roller coaster. I'm going to assume that that loop constitutes a circle of some radius, lowercase r. Now, in fact, loop-the-loop roller coasters are not designed as perfect circles. That's partly a safety issue. But right at the top of the arc, there is a curvature radius that if it continued in a full circle, you could assign that radius. So I've marked the radius r that's operating at the top of the loop-the-loop track. And the question is, how fast does that car need to be moving if it's going to make it all the way around that track? So there's its velocity vector and the associated magnitude of that velocity vector, its speed v. Let me ask a few questions before we start the mathematics of applying Newton's second law. First of all, what's the direction of the acceleration? Well, we learned in Lecture 6 about circular motion, and we saw that when an object is in circular motion, it's accelerating in the direction toward the center of the circle. When the car is right at the top of that loop, the center of the circle is directly downward, and so the answer to the question, what's the acceleration direction is, it's downward. What, therefore, is the direction of the net force? Well, Newton's law says F equals ma. The force and the acceleration vectors, they're in the same direction, and so the force, the net force, has to be downward. So the sum of all the physical forces acting on the car at the top of the track is downward. Now, that wouldn't be true somewhere else. There are 2 physical forces acting, and we'll see at some other points on the track they're in different directions. But at the top, the sum of all the physical forces acting has to be downward. So they have to be vertically oriented forces. So let's begin our procedure for applying Newton's second law. First, we write Newton's second law. That's our starting point for analyzing motion. We identify the forces on the roller coaster. What are those forces? Well, gravity is certainly acting on it. Gravity is always acting when we're near Earth's surface. There's also a normal force from the track. Just like that normal force I introduced before that is pushing up on the floor and keeping me from falling through the floor, anytime 2 surfaces are touching, there is a normal force between them, and that normal force is perpendicular to the direction of the surface that I'm standing on, or in this case, the car is in contact with, but in this case, that normal force is perpendicular to the track. So there's a normal force, which I'm going to call n with an arrow over it because it's a vector. So I'm going to rewrite Newton's second law with those two physical forces identified. Gravitational force, mg, normal force, n, and that's equal to the mass times the acceleration. The left-hand side, the real physical forces. The right-hand side, the mass times the acceleration. So here we are, Newton's second law for this situation, mg plus n, vector mg plus vector n is m vector a. Now, here's the interesting thing about this question. I have to ask, what does it mean to make it around the loop? It means that the car and the track are in contact. That means there's a normal force between them. If that normal force were to go to zero, the car would, at the instant the normal force became zero, lose contact with the track, and it would no longer be on the track. That's what happened when I launched my car with too low an initial height, and that gave it too low a speed going into the loop. So here's the point. If we want to get around the loop, and the car is going to be going slower and slower as it rises up because it's losing energy to gravity, more about that in the next few lectures. So right at the top, the very minimum condition for getting around the track is that the normal force just barely touches zero at the top. And then as soon as the car gets past the top, the normal force is going to grow again, and we're going to be in good contact with the track. So we could just barely tolerate going to zero normal force right at the top. And at that point, the only force acting is going to be gravity. So Newton's law is actually going to become simpler. It's going to become mg equals ma. Now, you wouldn't really want to be in the car with that small a margin of safety, because if anything goes wrong, you get a little bit slower, you're going to fall off the track. But that would be the absolute minimum condition for staying on the track. So mg is ma. So there we are. Newton's law now for this situation has been reduced to mg equals ma. And we'll take the convention, just in this case because we're talking about the forces being down and the direction of the force being downward, we'll take down to be positive. That's fine. The acceleration in circular motion we found in lecture 6 is the square of the speed divided by the radius. So that's the value of the acceleration in circular motion, and as a vector, that acceleration is directed toward the center. So I'm going to rewrite Newton's second law. mg is the force. ma is the acceleration, m times v squared over r being the acceleration. I've taken the vector signs off because I've assigned this convention that down is positive, and both these things are in the downward direction, the gravitational force and the acceleration. So there's Newton's second law. Notice that the mass cancels. We're getting used to that happening in situations involving gravity, and that's again because all objects experience the same gravitational acceleration regardless of their mass. And we can finally solve that. We cancel the m, we get v squared equals gr if I multiply through by r, and I take the square root, and v is the square root of gr. So there's the answer. If you're going at speed v equals square root of gr at the top of the loop, you're going to be okay. You're going to just barely get around that loop. If you're going any faster, there will continue to be a non-zero normal force. You'll feel pressed against the track, and everything will be fine. Going any slower than that, and you're going to lose contact with the track at the top of the trajectory, and you're going to fall off in a parabolic arc like a projectile, as we've seen before. So there is a fairly sophisticated Newton's law problem done out in all its detail, and it answers the question, how fast do we need to be going at the top of that loop? Let's do some numbers on that. Here's a particular loop-the-loop track, the Revolution at Six Flags Magic Mountain. The radius is 6.3 meters. If I work out my result, v equals the square root of gr. G is 9.8 meters per second squared, 6.3 meters. That comes out 7.9 meters per second, which is about 18 miles per hour. And the actual speed of that roller coaster at the top of its loop is 9.7 meters per second, and that gives you a margin of safety. So there is a rather sophisticated calculation, and it answers the question, why doesn't the roller coaster fall off the track? There is no reason for it to fall off the track. The question you really need to ask is the roller coaster's motion changing in the direction of the net force? Yes, it is. The net force is downward, and the motion is changing in the downward direction because it's in circular motion. And circular motion is toward the force is toward the center of the circle, the acceleration is toward the center of the circle, and we got more quantitative by using our expression for the acceleration in circular motion. Let me now give you a little quiz. So here is a picture that appeared on the New Yorker, a delightful picture of people riding a loop-the-loop track. And I would like you to pause a second and think about and answer in your mind the question, what's wrong with this picture? Okay, I hope you had a nice pause, and I hope your brain did some work on that. I'll tell you what's wrong with the picture. The passengers are in the loop-loop roller coaster. They're not falling out because the designers of the roller coaster have it going fast enough. The problem is they're having a bad hair day. Their hair is hanging downward. The artist has pictured the hair hanging downward. But the hair shouldn't be hanging downward. What's the direction of the net force? They're in that circular motion. The acceleration direction is downward. The net force is downward. All the forces that are acting on the objects in the roller coaster ought to be downward. And yet if the hair is pointing down, that implies the tension force in the hair holding it to the head is upward. That's the wrong direction for the force. The hair should be pointing upward. Down along the direction of the faces, but upward in this case. Why? Because everything is undergoing a downward acceleration, and there needs to be a net downward force on it. The roots of the hair need to be pulling downward on the ends of the hair. Everything in that roller coaster, when they're going through the loop, feels like the downward direction is up. That's what's happening. That's what people feel. Not because there's some mysterious extra force, but because the net force on them is downward and their acceleration direction is downward. Okay. Let's move on to some other examples. Here's an example that is commonly raised to illustrate somewhat the same point. What happens to your weight if you stand at the equator? What does a scale read if you stand at the equator? So I'm not going to do this one in all its quantitative detail, but I will work through it qualitatively. So here's a person standing on a scale at the equator and another person standing on the scale at the North Pole. What's the direction of this individual's acceleration? Well, the Earth is going around in a circular motion because of its rotation, so the direction of the acceleration is towards Earth's center. So the net force on that individual is toward Earth's center. It's not zero. It's toward Earth's center. What forces are acting? Gravity is pulling down toward the Earth's center. The scale is pushing up. Those two forces do not add to zero. In fact, the gravitational force has to be greater to make the net force be toward the center. And that means the scale force is less than the gravitational force. And since the scale reads what the force is that the scale is exerting, the scale reads less than your actual weight. So your apparent weight at the equator is less than your actual weight. Not so for the individual at the North Pole, who is not going in a great big circle with that kind of issue. So the person at the North Pole is going to weigh the same as they normally would, but the person at the equator is going to weigh, well, they're going to weigh the same as they normally would because weight is the gravitational force, but a scale is not going to read the same in that case. Okay, let's move on to a more sophisticated problem, because the problem about the roller coaster really ultimately, when we got to the top of the track, was a one-dimensional problem. So now we're going to do a real two-dimensional problem. So let's begin with a couple of movie clips here. Here we see an airplane turning. If you've ever been in an airplane, when it turns, you're suddenly looking out the window and the ground is right down there, or maybe the sky is up there, depending on which side you're on, because the airplane has to bank to turn. The reason it has to bank is because the aerodynamic forces that normally keep the airplane upward and are vertical have to have a component toward the center of the circle in order to turn the airplane. The other clip is of racing cars going around a banked track. Why is that track banked? That track is banked in order that the cars have a normal force that has a component toward the center of the circle to keep them from sliding off the track. Even if that track were covered in ice, if they were going at the right speed, they wouldn't need any friction to keep them on the track. So I'd like to do, again, a mathematical analysis of this banked turn issue. And I want to ask the question, what has to be the angle at which we bank, say, a road in order for cars to be able to get around it without having to rely on friction to keep them on the road? So let's begin. Do this one a little bit faster because now we sort of get the feel for Newton's law. So the question is, here's a banked highway. We're looking at it head on. Here's a car coming at us. The angle of the banking is theta, and we want to know what that angle has to be. And we have to begin by thinking about the direction of the acceleration. It's toward the center of the turn. The car is executing a turn like this. The center of the turn is that way. So the direction of the acceleration is toward the left. So the net force must be toward the center. It's horizontal. It's that way. What are the forces acting? Well, we write F equals ma. We ask about those forces. They are the gravitational force, mg, always acting. They are the normal force from the road, perpendicular to the road. But now perpendicular isn't vertical. Perpendicular is, in fact, perpendicular to the road, so it's at that angle. And you'll notice what is going on here. If the car is not to be sliding along the road, the vertical component of that normal force, the vertical part of it, has to balance gravity. The horizontal part, which is giving just the net force, there's no gravitational component in the horizontal direction, gravity is purely vertical, has to be pointing to the left. And that's what's providing the acceleration of this car as it goes around the turn. Newton's second law for this case then reads, vector mg, the downward vector, plus the normal vector equals ma. So we've gone through all that. Here's Newton's law for this situation. Gravitational force plus normal force equals ma. It's the same equation we had before. Let's take the convention that positive in the horizontal direction is toward the center of the circle. The acceleration in circular motion, as we know, is the square of the velocity divided by the radius. So there we are. And now let's pause and take a brief look at trigonometry as I outlined much earlier in the course. Here's a review of trigonometry. Remember, it's about right-angled triangles. So if we have a right-angled triangle with some angle theta, the sine of that angle is defined as the opposite side over the hypotenuse. The cosine of the angle is defined as the adjacent side over the hypotenuse. We need trigonometry in this problem because we need to find out the two components of that normal force, horizontal and vertical. So if we work that out, if you look at the angle theta here, you'll see that's really the same as this angle. These are similar triangles. So there's the same angle theta. And the horizontal component is the opposite. So the horizontal component over the normal force is the sine. And so the horizontal component of the normal force is n sine theta. There is no horizontal component of gravity. So n sine theta is mv squared over r. In the vertical direction, let's take positive upward. Minus mg is the gravitational force. N times the cosine of theta, the adjacent side here, adjacent to that angle theta, is the component of the normal force. So those add up to 0. And that lets me solve for n. N is mg over cosine theta. And I can stick that into there, and then I've got my solution. So here are my two equations. The horizontal equation describing Newton's law, the forces in the horizontal direction. The vertical describing the forces in the vertical direction. I've solved the one of them for n. I'm going to plug that into n. Substitute the vertical into the horizontal. I get mg sine theta over cosine theta. N is mg over cosine theta. Mg sine theta over cosine theta is mv squared over r. As usual in problems involving gravity, the mass cancels. Mass doesn't matter. That's a good thing because it means a big truck and a small car. The same banking angle holds for both of them. So if you're a highway designer, you can design a highway with the same angle. Solve that, we get that the tangent of theta must be v squared over rg. So you tell me the velocity you want cars to go at on this corner. You tell me the radius you're willing to build this highway turn. That's the answer for the banking angle you should make. If you make it that angle, cars moving at that speed will not need frictional forces at all to hold them in their turn. They won't go skidding off the turn. If they go too fast, they'll go skidding off. If they go too slow, they may go skidding down. But if they go at just the right speed, they will be held there by the normal force alone. Now, of course, there is some friction against the tires and the road, and that will allow people to go at different speeds. But this is a safety thing that makes the optimum speed be one where the frictional force is not needed. Although I talked about this in the context of a highway, the result is the same even if we talked about, say, an airplane and the angle at which the airplane has to bank, because it's the same thing. The normal force in that case is perpendicular to the wing, and it's the aerodynamic lift forces instead of this push, which is the normal force from the road. But we'd get the same answer. So this is actually quite a universal result. And we have done now a rather sophisticated Newton's second law calculation. Really, in two dimensions, we ended up with two different equations representing the two different components of Newton's law in the horizontal and the vertical direction. And when you're working a problem like that, you have to work with generally two equations, and you'll end up having two unknowns. In this case, we not only didn't know the angle which we were trying to solve for, but we also didn't know the normal force. We weren't asked to solve for that, but in the process, we had to find it, because we had to substitute in the other equation to get rid of it. So we were able to get down to the answer for what we wanted to know. So that is a sophisticated two-dimensional Newton's second law calculation. Well, let me wrap up what we've talked about here, but I would like you, if you would like a mathematical challenge, to go a little bit further. So we ask the question, why doesn't the water fall out of the bucket? Why don't the people fall out of the roller coaster? Why doesn't the car slide down the bank turn or slide up the bank turn? How can the plane fly tilted? Those are all really the same question. And in a sense, they're all the wrong question. And they're the wrong question because force and motion are related in that force causes change in motion. Force does not cause motion itself. Don't expect things to move in the direction of the force exerted on them. That's what Aristotle said. And Aristotle was wrong. And for 2,000 years, that wrongness was perpetuated. But that's wrong. What force does is to cause change in motion. And in all these cases, the water in the bucket, the car on the loop-the-loop roller coaster, the vertically rolling ball, the car on the slope track, the airplane with its wings tilted, in all those cases, the object's motion is changing, undergoing some kind of circular or curved path, in exactly the direction of the net force on it. And Newton's law gives us all that completely quantitatively by telling us exactly how the force and the acceleration are related. Do not expect things to move in the direction of the force. Once in a while, a simple case like just dropping an object, they will. But if the object already has some velocity, and the velocity isn't in the same direction as the force, then the object is not going to move in the direction of the force. Its motion is going to change in the direction of the force, and Newton's law will be perfectly happily satisfied as it is for all those cases we discussed in this lecture. Now, if you don't want to do a lot of math, you're done. But if you would like to take a math challenge, here's the challenge I want to pose for you. So I'm going to take a ball, and I'm going to whirl it around on a string horizontally like this. And if you look closely, you will notice that the ball is not perfectly horizontal. The string is not perfectly horizontal. If I make the ball go faster, the string gets more horizontal. If I make the ball go slower, the string gets less horizontal. But it's not perfectly horizontal. In fact, it couldn't be. If it were, there would be an infinite tension force in the string, and that would be impossible. So here's your challenge. You got the ball whirling at the end of a string. The string length I'm going to call L. The maximum tension in the string before it breaks, I'm going to call T sub break. So strings, cables, things like that, they have breaking tensions. If you apply more force than that, they fail and they break. I would like you to find an equation for the maximum speed, Vmax, that ball can have as it whirls in its horizontal circular path. And I want an equation in terms of just the string length L, the ball's mass M, the breaking tension T break that I just described, and the other obvious thing that's working here, gravity, as expressed in the gravitational acceleration G. Now, if you look in my diagram, I've indicated the angle theta here also. And that's an important parameter in what's going on in this problem. That angle changes with the speed. But I don't want that angle to be in the final answer. I want the final answer just to contain the string length L, the ball's mass M, the breaking tension T break, and the gravitational acceleration G. If you can do this problem, you're pretty good at algebra and a bit of trigonometry, and you also really understand how to apply Newton's second law in 2 dimensions. So take a moment and work that problem, or maybe more than a moment. It might take you 10 or 15 moments, and I'll come back and give you the answer. Okay, here's the answer to the problem. Looks a bit complicated. The maximum speed turns out to be the square root of the length times the quantity, the square of that breaking tension, minus the square of the weight, mg, divided by the mass times the breaking tension. I'm not going to show you how I got that. You'll have to work that out if you want to do that. But let me just ask if this makes sense. What if the breaking tension happened to be equal to the ball's weight? The ball's weight is mg. If T break were mg, then that term in parentheses, T break squared minus mg squared, or m squared g squared, would be 0. And that would say the maximum speed would be 0. And of course that makes sense, because if the breaking tension were the ball's weight, then just hanging the ball like this would be enough to break the string. I couldn't even begin to think of adding more tension by whirling it around. So our answer certainly makes sense in that special case where the breaking tension is equal to the ball's weight. And if the breaking tension is bigger, this is going to give us a positive answer. And that's going to tell us we'll be able to whirl the ball around with some speed. But if we whirl it too fast, bye-bye ball, because the string is going to break and the ball is going to go off on a straight line at constant speed, eventually describing a parabolic trajectory vertically under the influence of gravity.